Hi, I'm Howard.
Hi, I'm Xiaohan.
Hi, I'm Wotao. Several applications require repeatedly solving the same problem with different data. Learned algorithms, which are data-driven, may be fast but fail to converge. Classic hand-built optimization algorithms may be slow but will converge when their explicit conditions are satisfied. Safeguard L2O algorithms take the best of both worlds, can be fast and converge. Consider minimizing a function where v is its data, x is what we have to decide. Most classic optimization algorithms is a fixed point iteration, generating a sequence xk that asymptotically minimizes f. L2O or learning to optimize update can be anything, for example, a trained neural network. We introduced the safe L2O scheme, which uses a condition to determine whether to take the L2O update or to fall back to the classic update at each iteration. Our safe L2O scheme can be applied to solve many convex problems and enjoys the following properties. It uses only known quantities related to the convex problems, such as objective values and gradient norms. L2O and safe L2O schemes will perform identically on good data with comparable per iteration costs. The safeguard kicks in only when bad L2O updates would otherwise occur. Safe L2O also ensures worst-case convergence guarantee similar to analytic algorithm.
We propose the following safeguard scheme. Consider a non-negative number mu k and a classic update operator t from an optimization algorithm. Now, we say that a vector y is a good update to xk provided the following holds. We need the fixed point residual and the distance between y and our current iterate xk to be small. We quantify the fixed point residual as the norm of our y minus the update operator applied to y. We quantify the distance between y and xk in the second term. Notice there is a beta here, and this is a scalar that is non-negative and used to weight the relative importance between these two terms. Now we say that this is small provided that it's less than or equal to alpha times mu k. Alpha is set to be some number between 0 and 1. Throughout, we'll let yk plus 1 be the L2O update for xk. If it is good, then we accept it, and we set xk plus 1 to be yk plus 1. Otherwise, we set xk plus 1 to be equal to t of xk. Now let's consider how to update mu k. Here we show an example with an exponential moving average, where we fix theta between 0 and 1, and we update the safeguard value mu k via multiplication by 1 minus theta. Then we add to this theta times the expression we saw above. Because alpha is between 0 and 1, this update mu k plus 1 will now be a geometric factor less than the current iterate mu k. We can code the safe L2O scheme as follows. In line 1, we input data d. In line 2, we used fixed initializations of mu1, x0, x1, and k equals 1. In lines 3 through 10, we use a while loop. This is used to iteratively update our xk until we reach convergence. A single example of convergence is shown here as an update residual, although others may be used. Now, in line 4, we see an L2O update is applied to xk. If this update is good, as measured by our safeguard condition in line 5, then we apply it in line 6. That is to say that if this safeguard condition is satisfied, then xk plus 1 is equal to our L2O update. Otherwise, xk plus 1 is given by applying the classic update operator t to xk. In line 9, we see that we update the safeguard mu k to get mu k plus 1. In line 10, we update our counter k, and then in line 11, we return our solution estimate xk. A key result that we provide is to show that if a sequence xk is generated using the safe L2O update scheme and one of our proposed safeguards, then it will provably converge to a solution of the optimization problem. This is important because it does not assume any structure whatsoever on the L2O updates. Rather, we use a structured safeguard sequence of mu k's to steer the sequence towards convergence. We next turn our attention to some experiments that show the effectiveness of this approach.
We conduct numerical experiments on several optimization tasks to verify the efficacy of our safeguarded L2O. In each task, we try to recover some hidden variable x from the observable data d by minimizing an objective function f. In the first task, we have a dictionary A, which is a short and fat matrix that is generated beforehand and fixed. We assume that the hidden variable xd star that we would like to recover is sparse, and the data d that we can observe is its noisy linear measurement under dictionary A. The objective function that we minimize over is the L1 regularized least square, which is also known as the Lasso model. Because the dictionary A is fixed, the distributions of the sparse signals xd star and the noises decided the data distribution in this task. We assume that all training samples are independently drawn from this data distribution, which we call the scene distribution. As the typical assumption of most machine learning problems, the testing samples are drawn from the same distribution. However, in this work, we assume that some testing samples could come from a different distribution that is unseen during training, which is very likely to break the L2O schemes without a safeguard. We use A-lista as the L2O scheme for the first task of sparse recovery. The figure on the left shows the superior performance of the L2O scheme over the classic ISTA update on the scene distribution. In contrast, the figure on the right shows the performance of the L2O scheme with and without the safeguard on testing data from the unseen distribution. We could see that ISTA always converges as guaranteed, and safe L2O is aligned with L2O without safeguard for the first several steps. However, when the L2O scheme makes catastrophic mistakes, the safeguard kicks in and keeps it from diverging. Besides synthesized data, we also apply safe L2O to natural image denoising task. We train a listener model on natural images corrupted by Gaussian noises, and then apply the trained model to pepper and salt noisy images. We can see that safe L2O successfully prevents lista from diverging. We further include the dictionary A as part of the inputs that can vary among different samples. We adopt AdaLista as the L2O scheme, which is designed for this scenario, and our observation is consistent.
To recap, L2O algorithms can quickly solve optimization problems with new but similar data, but may not always converge. We have introduced safeguards to make sure they converge with very little loss of performance. Thank you for watching. Check out our paper for more details.